Hey everybody, I'm going to go over substitution and elimination introduction in this video. So this is going to be kind of introducing these topics. And I apologize, I've kind of got a little bit of a cold right now, so I'm a little rough sounding, but we'll get through it. Okay, so the first thing that we need to do is recall our nomenclature from alkyl halides, right? So if I have a primary alkyl halide, I've got that carbon that has some sort of halogen on it. And then that carbon has one carbon on it. Secondary is going to have 2 carbons on it. Tertiary will have 3 carbons on it. And then we also have kind of a couple special ones, which are the allylic halide and then the benzylic halide. Both of them are alkyl halides, but kind of special examples because we've got those sp2 atoms right next to it. So we also want to be thinking about our dipoles. Okay, so if I have this ethyl bromide here, we would be looking at a dipole with the carbon and the bromine. Okay, so I've got pulling electrons towards that bromine. That bromine is delta negative. This carbon is delta plus. Okay, the delta plus carbon is going to be the most important thing that we're looking at here. Keep in mind too, when you're looking at dipoles, obviously if you have a delta plus, you probably have a delta minus. So this bromine, it's tempting to kind of look at it as a nucleophile right now, but we don't really want to be doing that because bromine doesn't want another bond right now. Okay, bromine would be totally happy having all of the electrons of that carbon-bromine bond, and that's how we're going to see the halogens function is as leaving groups. And we can see them function as nucleophiles, and we'll talk about that a little bit as we get going a little bit later as well. Okay, so making sure that we are clear here that that carbon, that is the electrophilic carbon. Okay, and that's where our reaction is going to take place. Okay, so let's start off by looking at substitution and elimination and just kind of what they are first. Okay, so this is a couple of reactions that you might see if you were just looking up substitution elimination. So if I've got something like sodium hydroxide here, the first thing that I tend to do is I see sodium and I put a plus on it. So that means I have to put a minus on my oxygen. And I know that that's basically going to be a lot more ionic because we've got kind of left and right sides of the periodic table together. So it's going to be a lot more of an ionic bond. So we can just think about it like this. You can cancel out the sodium if you want and just use the OH minus. I don't care if you do that. That's totally fine. Okay, so in an SN2 reaction, we're going to see that OH come and substitute for that bromine. Okay, so this is a substitution reaction. And then the other product that we're going to be making is sodium bromide, okay, NaBr. So this is a substitution. And hopefully you can see how we got to that name because we substituted OH for the Br. Okay, so our nucleophile is our OH minus. We've got this carbon as our electrophile. And we're making a bond between the nucleophile and our electrophile, and then kicking off our leaving group. And we will talk about arrows in just a second. Okay, so this is the basic substitution reaction. Anytime you're substituting a nucleophile and a leaving group, that's going to be termed as a substitution reaction. They are very, very common reactions. So this one in particular is named SN2. Okay, so the S stands for substitution. The N stands for nucleophilic. And then the 2 stands for bimolecular. Okay, and the bimolecular part, the only thing that that's really saying is that we have 2 molecules interacting in our rate determining step. Okay, so when we're looking at this, substitution nucleophilic, right? We've got a substitution reaction happening. We're using a nucleophile, and we have 2 molecules involved in that step to make that happen, okay? So that's your SN2. But if we're looking at this, we don't usually look at sodium hydroxide and just think nucleophile. Hopefully you kind of gotten to the point where you're looking at sodium hydroxide and going, base, that's definitely a base, and we can definitely use it as a base, okay? So if we do an acid-base reaction instead, okay, so if I do an acid-base reaction instead and have that hydroxide go for a proton, I'm actually going to end up getting an alkene product out, plus sodium bromide, plus water. Okay, and that's going to be our elimination reaction. So this is an elimination. Just scooch this down a touch. Okay, so E stands for elimination. And 2 is again for that bimolecular. Okay, so mechanistically very similar in terms of the bimolecular part, where our rate determining step is going to have the 2 molecules interacting. Same 2 molecules in this case. And then the big difference is really that we're eliminating our leaving group and not replacing it with something new. Okay, so we're just getting rid of it and putting a new pi bond down instead. So that's going to be our elimination process. So let's look at comparing SN2 and E2 a little bit more. So an SN2 reaction, this is just kind of a general reaction scheme. We have some kind of nucleophile and we've got some kind of alkyl halide here. And I can go with my nucleophile and we're going to come attack right at that electrophilic carbon. And then we're going to push our leaving group off. Okay, so this is a nucleophilic attack and loss of leaving group step. So that's going to get me to my new product. And then my leaving group as an anion. Okay, and generally, yes, it's going to be kind of in a salt form with whatever other counter ion you had. That's totally fine. Like I said, here I don't really care too much about the counter ions, so we can kind of skip it if you don't want to deal with where it's all going. Okay, so if we're looking at SN2 reactions, we want to really take a look at our alkyl halide and what kind of alkyl halide we have. So a primary alkyl halide, it works great for SN2. Okay, but then you start getting to secondary and then it's kind of okay. And then you get to tertiary and it's not happening at all. Okay, so if we stop the share real quick, we look at a model, we can kind of see how that works. So this is just ethyl bromide, right? I'm just having the red is my bromine right now, just because that's the color that I had out. So if I've got a nucleophile, if we kind of envision the same arrow situation that I just drew on the screen, if I have my nucleophile come in, I need to come right here. So this is where my nucleophile is going to be attacking, because I have to come from the opposite side of this leaving group. Okay, so my leaving group here, I have to come opposite that to be able to actually make a new bond. So because of that, this area has to be pretty open and available. So anything that makes it really crowded, it's going to hinder your nucleophile being able to actually access the electrophilic carbon. So if you look at a tertiary alkyl halide, this is what we're looking at. We'd have to be coming through all of this garbage to get to this electrophilic carbon. So the more steric bulk you have around the electrophilic site, the less likely you are to be able to actually do an SN2 reaction. Okay, because there are other things that it could do instead that are way easier and way faster. So why is it going to actually go through all the effort of doing that? It just won't. So that's something to keep in mind. Super, super heavily based in sterics for SN2 reactions. Alrighty, let's get the share back up. Alrighty, so that's kind of what's going on with our primary, secondary, tertiary, is we want to really keep an eye on on making sure that we're looking at the right thing, okay? And keeping in mind here, very, very important that this is only for sp3 electrophiles. Okay, for a very similar reason that when you have sp2, what you're essentially getting here, oops, that went crazy. So if I've got a pi bond there, I have a p orbital right here, and that's going to be blocking access in its own way because it's got a whole cloud of electron density there. Okay, so this is essentially blocked. So we're not going to see any SN2 or E2 on these, on anything besides sp3, so sp2 or sp atoms. Okay, so we want to make sure that we're being very clear about that pi or that p orbital is blocking that nucleophilic attack, so it's not going to happen. Okay, so if we look at the other significant properties of an SN2 reaction, stereochemistry is going to become a really, really big one. Okay, so if I'm attacking directly opposite of my leaving group every time, this is going to result in an inversion of stereochemistry. Okay, so the new bond is going to form on the opposite side of the leaving group. Okay, you will often abbreviate leaving group as LG. So that kind of makes sense if you're thinking about somebody walking through a door. It's easier for somebody to walk behind the door as they're walking out instead of trying to walk through the person and getting through the door. So always going to be coming from the opposite side of your leaving group. And so it's going to be installed on the opposite side of your leaving group as well. In this case, because this is not a stereocenter, I could redraw this any way that I want. So it really is only going to matter if you have a stereocenter. Otherwise, you won't really notice the inversion because it will just be happening on an achiral carbon anyways. Okay, so what leaving groups we can use? We've got iodine, bromine, and chlorine. Okay, so any of those three halogens are going to work fine. It's going to be iodine is the best, chlorine is kind of the worst, and we'll talk about leaving groupability as well at some point. But these are the ones that work. Fluorine is never going to be a leaving group, so just keep an eye out for that. It's never going to be used as a leaving group here. And then strong nucleophiles. Okay, so notice how when we had this nucleophile, we had a minus on it. When we did this reaction up here, we had an O minus. So we're looking for a really strong nucleophile that's got some good localized electron density and is fairly reactive. Okay, so we're looking for a strong nucleophile. So some examples that you might run into, you might see OH minus with various counter ions, OR minus, OET. So that OR minus is going to be like OET minus, OME minus. You can have this happen with alkynes that have been deprotonated, right? Because those are the acidic protons there. Those are going to be kind of the strong nucleophiles that we might see in an SN2 reaction. And we're going to learn some more special ones a little bit later so that we can kind of get some better selectivity, because we're going to run into some problems with that, as you will see later in this lesson. Okay, so that's going to be our SN2 reaction, but you really need to beware here. Okay, because SN2 and E2 reactions often occur together. Okay, they are competitive with each other. So if we have a reaction that's competitive, that means that we're kind of having whoever's going to be the faster reaction is generally going to be what you're going to see as the major product. So that's going to come up a lot as we get into as we get more into these reactions. All right, so let's look at E2. So this is kind of the basis for an E2 reaction. We need to have some kind of strong base and then our alkyl halide. For E2, we're kind of in an opposite situation as compared to the SN2. because in this case, my base doesn't need to access the electrophilic carbon, it just needs to access a proton. That's much, much easier to accomplish. Okay, so my base is going to go grab this proton. So that's just a typical acid base step. Instead of forming that CH bond into a lone pair, the more stable thing to do is to throw it into a pi bond and then kick off our leaving group. Okay, so this is a 3-arrow process, all 3 arrows happening at the same time. And so we've got our R group. We still have one H down there. And we have our new conjugate acid and our leaving group that was expelled. Okay, so that's going to be a basic E2 reaction. So for alkyl halides, in this case, because we're kind of opposite, the primary alkyl halide is actually going to be okay. It's not great. It's definitely not awesome. But as you get into higher levels of steric hindrance, where you're starting to block access to the electrophilic carbon and making it more likely for the SN2 reaction to have trouble, that's when our E2 starts getting really good. So a secondary is pretty good. And then the tertiary is going to be really good here. Okay, so this is going to happen 100% of the time instead of SN2. Okay, so if we've got a tertiary alkyl halide and you're throwing in a strong nucleophile or strong base, you are going to end up getting E2 rather than getting any kind of substitution product. You're going to start making alkenes for sure. Okay, so if we're looking at the other characteristics of an E2 reaction, we're looking at stereochemistry. This is a little bit weirder, where the H and the leaving group have to be anti-periplanar. Okay, and all that means is that they need to have a 180-degree dihedral angle between them. Okay, so if we're looking at a Newman projection, say, we would need to have our X and our H 180 degrees apart in the anti-positions to each other. Okay, and they have to be in the same kind of plane. So that's the periplanar part, anti and periplanar. Okay, so I'll be talking about how to do that in another video. This is just kind of the introduction, so we're gonna just try to keep it shorter and not crazy. All right, so that's our stereochemistry. For our leaving groups, we're gonna have all the same leaving groups here: iodine, bromine, chlorine. For nucleophiles, we're gonna see very similar nucleophiles here. It's nucleophiles that can also be bases. Okay, so we're going to see pretty frequently that nucleophiles and bases have a lot of overlap between them. We're going to see some where there isn't overlap, but the ones that I've got on here right now are going to have a lot of overlap, where we can have stuff like OH minus, OR minus. We can have that alkyne. Okay, those are all going to be pretty strong in terms of bases, and they will also be strong in terms of nucleophiles. So this is definitely the ones where you're going to see most of that competition occur. So that's kind of the overview of our SN2 and E2 process. I'm going to post another video that has an example worked through so that we can kind of see what it looks like in real time, and talk about how exactly you go about the anti-periplanar business and all of that stuff. So as always, let me know if you have any questions, and I'll see you all later.